Hi students, here is your fourth lecture, distribution of molecular velocities. In the context of kinetic molecular theory of gases, a gas contains large number of particles in rapid motion. Each particle has different speed and each collision between particles changes the speed of particles. An understanding of the properties of the gas requires an understanding of the distribution of particle speeds. The distribution of molecular speeds or velocities is given by Maxwell and Boltzmann and is usually called Maxwell's distribution of molecular velocities. It is used to determine how many molecules are moving in a range of velocities. If we plot the fraction of molecules having velocities fall within a narrow range v and v plus dv, where dv is an infinitesimally small increase in velocity from v against velocity, we would obtain a slightly asymmetric curve known as Maxwell's velocity distribution curve. Here you can see three curves. These three curves denotes the distribution of speeds for the gas at three different temperatures T1, T2 and T3, where T3 is greater than T2, which is greater than T1. The main features of Maxwell's distribution curves are: at lower temperature, most of the molecules have less energy, therefore the speeds of the molecules are lower and the distribution shows a narrow peak. The peak of this curve corresponds to most probable velocity, which is the velocity possessed by maximum number of molecules. For the three curves, we have three most probable velocity values. As the temperature increases, the curve flattens out because high temperatures allow a large fraction of molecules acquire greater speeds. These are the main features of Maxwell's distribution curve. Next, we have an equation which is derived by Maxwell and Boltzmann, which forms the basis of kinetic theory of gases. It defines the distribution of speeds for a gas at a certain temperature, and the equation is in the form dN by n equal to m by 2 pi kb T raised to half into e raised to minus mv square by 2 kb T into dV, where dN by n is the fraction of molecules moving with velocity v to v plus dV. M is the mass of the molecule, kb is the Boltzmann constant, T is the absolute temperature. From this distribution function, three types of velocities or speeds of a gas can be derived, which are most probable velocity, average velocity, and root mean square velocity. The most probable velocity is the velocity possessed by maximum number of molecules at a specific temperature. We have seen it in the graph, and it is easily calculated by the equation derived from Maxwell-Boltzmann equation, that is VMP, most probable velocity, equal to root of 2 RT by M, where R is the universal gas constant, T is the absolute temperature, and M is the molar mass of the gas. Next is the average velocity. It is the sum of the speeds of all the molecules divided by total number of molecules, and it can be obtained by the equation V average equal to root of 8 RT by pi M, and the root mean square velocity is the square root of mean of squares of the velocity of individual gas molecules. By calculation, it is very tedious process, but from Maxwell-Boltzmann equation we would get a simple equation as Vrms equal to root of 3 RT by M. If we know the molecular mass at a specific temperature, we can easily calculate the root mean square velocity of a gaseous system. These three equations are very important, and as the three are nearly similar, you may get confused, so study well the equations. And you have an assignment today. You have to answer this question with your justification and submit as an assignment on Saturday. By this, I am concluding the lecture. Thank you, dear students.